Here in this lesson, we will develop a brand new definition of our trigonometric functions. In previous lessons, we defined the 6 trigonometric functions based on angles that are in standard position. Just a little recap, an angle is in standard position if the vertex is at the origin and its initial side is on the positive x-axis. Here in this lesson and in the lessons to come, we have a brand new definition for our trig functions, and it is a right triangle based definition. So here we will define our 6 trigonometric functions as ratios of the lengths of the sides of right triangles. So here I have shown you in this diagram an acute angle. Let's call it angle A. This is an acute angle A, and notice that angle A is in standard position. And like usual, I've drawn the perpendicular from point B that's on the terminal side of our angle down to the x-axis, making a right angle here and a right triangle, triangle BAC. Now this distance here from the origin to point C here is x, and the distance from point B on the terminal side down to the x-axis, this distance here is y, and then this distance here from the origin to point B is r. But more than that, I think what I really want to highlight is this side length y. It is opposite angle A. This side of length y is the side that's opposite angle A. And the side of length x here is adjacent to angle A. Adjacent meaning it's sharing a side. So this side of length x is adjacent to angle A. This side of length y is opposite angle A. And of course, this side of length r is the hypotenuse of your right triangle. The definitions that I'm about to give you now are going to be ratios of these lengths. And here it is, sine of angle A. Remember, angle A is the acute angle A here. Sine of angle A now is y over r. Now this is the definition that you and I have already discussed in earlier lessons. But notice that it's y over r, which is the side that's opposite angle A over the hypotenuse. I've abbreviated opposite as OPP and hypotenuse as just HYP. So sine of angle A is equal to this ratio, the side opposite angle A over the side, the hypotenuse of the right triangle. Look at y over r. So it's the side opposite angle A over the hypotenuse. Cosine of angle A, we know as x over r, is the side that's adjacent to angle A over the hypotenuse. Tangent of angle A, we've known it as y over x, happens to be the side opposite angle A over the side adjacent to angle A. Cosecant, secant, and cotangent of angle A are all reciprocals of what we just mentioned. Some students have used SOHCAHTOA to help them remember this definition. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. SOHCAHTOA. It's up to you whether you find that helpful or not. If you do, go ahead and use it. If you don't, well, just pretend I never said it. Okay, awesome. Let's move on and do some work. All right, everybody, find the sine, cosine, and tangent values for angles A and B in this right triangle. Both angles A and B are acute angles, and we want to find the sine, cosine, and tangent values for angle A and for angle B. So let's go. Let's start with angle A. Now remember how sine of angle A is defined. Sine of angle A is opposite over hypotenuse. So here we're talking about sine of angle A. So the side that is opposite angle A is 36. and the hypotenuse is 85. So it'll be 36/85. This is sine of angle A. Cosine of angle A will be the side that's adjacent. So it cannot be this side, everybody, because this is already identified as the hypotenuse. So this is not the adjacent side, it's this side. This is the adjacent side for angle A. So it'll be 77/85. Adjacent over hypotenuse, 77/85. Finally, tangent of angle A will be opposite over adjacent. Opposite over adjacent, 36/77. All right, so those are the function values for sine, cosine, and tangent for angle A. Now let's go to angle B. So we have sine of angle B, we have cosine of angle B, and tangent of angle B. Now this is the perfect spot to pause the lesson, pause the video right here, please, and write down the ratios, write down the answers here. Find sine of B, cosine B, and tangent of B. Would you, on your own? All right, let's compare answers. I got sine of angle B is 77/85. Cosine of angle B is 36/85. And tangent of angle B is 77/36. All right, before we run to the next example, I want to highlight something. I don't know if you noticed. Notice that sine of A is equal to cosine of B. Notice that cosine of A is equal to sine of B. That's interesting, isn't it? Sine of A is the same thing as cosine of B. And cosine of A is the same as sine of B. Let's explore that pattern, and let's see if we can develop or derive an important fact. All right, I've given us a right triangle with acute angles A and B. I want to highlight something. Notice that the side that's opposite angle A, I've labeled as lowercase a. And the side opposite angle B is side B. The side that's opposite angle C is labeled lowercase c. So we always follow that pattern when we label our triangles, okay? Side A is opposite angle A, side B is opposite angle B, side C is opposite angle C. All right, can you please write down what is sine of angle A? What's sine of angle A? Sine of angle A is opposite over hypotenuse. And the side that's opposite angle A is A, and the hypotenuse is C. A over C. A over C. Now what I want you to realize is, what is cosine of angle B? Cosine of angle B. Well, here's angle B, and cosine is adjacent over hypotenuse. Adjacent over hypotenuse. Oh, it's the same thing, A over C. So notice that sine of A, sine of one acute angle is equal to cosine of the other acute angle. Let's dig deeper. Watch this. What's tangent of angle A? Tangent is opposite over adjacent. So for angle A, opposite is A over adjacent, A over B. Now watch this. What's cotangent of angle B? Well, here's angle B, and cotangent is adjacent over opposite. It's A over B. So what we just figured out is that this pattern continues. Tangent of one acute angle is equal to cotangent of the other acute angle. Now for a right triangle, we know that the two acute angles, A and B, are complementary, right? Because the three angles within this triangle must sum to 180 degrees, and angle C is already 90 degrees, that must mean angles A and B, these two acute angles, are complementary. They must sum to 90 degrees. They are complementary. A and B are complementary angles. So what we just determined is that sine of angle A is equal to, let me point right here, sine of angle A, watch this, is equivalent to cosine of its complement. A and B are complements. Tangent of angle A is equal to cotangent of its complement. Sine and cosine are called cofunctions. Tangent and cotangent are called cofunctions. These are cofunction pairs. Also, secant and cosecant are cofunction pairs. Let me write that down for you. So we have these cofunction pairs, sine and cosine, tangent and cotangent, secant and cosecant. These are cofunction pairs. And what we just established is that sine of an acute angle is equal to cosine of the complement of that angle. So for example, sine of angle A, let's assume that A is acute, okay, is equal to cosine of the complement of angle A. How do we write a complement? Well, we talked about this the other day in an earlier lesson. The complement of angle A is 90 degrees minus A. 90 degrees minus A is the complement of angle A. If you don't believe that, go ahead and add angle A to 90 degrees minus A, and when you sum these two, you will get 90 degrees. They're complements. So sine of an angle, acute angle A, is equal to cosine of its complement. In words, we can say cofunction values. Remember, sine and cosine are cofunctions. Cofunction values of complementary angles are equal. You may want to write that down for your notes. Cofunction values of complementary angles are equal. Here is the conclusion. Here is your list, your formal list of cofunction identities. Sine of angle A is equal to cosine of its complement. Cosine of an angle A, remember A is an acute angle. Cosine of angle A is equal to sine of its complement. Tangent of angle A is equal to cotangent of its complement. Cosecant of angle A is equal to secant of its complement. Secant of angle A is equal to cosecant of its complement. Cotangent of angle A is equal to tangent of the complement of A. Let's put this into use. All right, check this out. Write each function in terms of its cofunction. All right, and first notice that all of these angles that are given are acute. 9 degrees, 76 degrees, and 45 degrees are all acute. So what we can do is we can say sine of 9 degrees is equivalent to cosine of its complement. Cosine of 90 degrees minus 9 degrees. In other words, sine of 9 degrees is equivalent to cosine of 81 degrees. That's it. Sine of 9 degrees is going to be the same as cosine of 81 degrees. Punch it into your calculator. You will see that cosine of 81 degrees is the same value as sine of 9 degrees. Sine and cosine are cofunctions. 9 degrees and 81 degrees are complements. Cofunction values of complementary angles are equal. Cotangent of 76 degrees is equal to tangent, that's its cofunction, of the complement of 76 degrees, which we can find by subtracting 76 degrees from 90 degrees. So tangent of 14 degrees is equivalent to cotangent of 76 degrees. Cosecant of 45 degrees will be equivalent to secant of 90 degrees minus 45 degrees, which will be secant of 45 degrees. So this is cofunctions and their values. Find one solution for the equation. Assume all angles here are acute angles. Now, notice that we have cotangent of theta minus 8 degrees is equivalent to tangent of 4 theta plus 13 degrees. Notice that cotangent and tangent are cofunctions. And we already proved, we have already stated that cofunction, watch this, cofunction values of, here it is, complementary angles are equal. Cofunction values of complementary angles are equal. So the only way this statement can hold, the only way this left-hand side will be equivalent to the right-hand side is if this argument and this argument are complements, are complementary. Because cofunction values of complementary angles are equal. So this angle and this angle must be complementary. In other words, they must sum to 90 degrees. That's the only way this left-hand side will be equivalent to the right. So I've taken these arguments and I have summed them to 90 degrees because that's the only case in which this statement will hold. All right, so I can go ahead and combine like terms. 4 theta and 5 theta is, 4 theta and 1 theta is 5 theta, and negative 8 degrees and 13 degrees is 5 degrees. I'll subtract 5 degrees from 90 degrees, and I'll divide both sides by 5, and theta must be equal to 17 degrees. This is the solution for theta. If you were to plug 17 degrees in for theta, you would find this left-hand side is exactly equal to the right-hand side. All right, let's study how function values change. Here I've shown you 3 different right triangles. From left to right, the length of each hypotenuse is the same. Well, it's supposed to be the same, okay? So as you go from left to right, this hypotenuse is supposed to be the same length as this hypotenuse and the same length as this hypotenuse. But what is changing is angle A is increasing in measure. So here's angle A, and then it's getting wider and then even wider, okay? And notice that as angle A increases in measure from 0 degrees to 90 degrees, right? It's getting bigger and bigger and bigger. The length of the side opposite angle A is increasing, right? So look how Y increases and increases as angle A increases. As A increases, Y is increasing. As A increases, Y increases, but R is fixed. R is fixed. That leads me to believe that sine, the sine function, is an increasing function because if the side opposite angle A, which is Y, if it is increasing as A increases, as angle A increases, side of length Y is increasing and R is fixed. And when in this fraction, if the numerator is getting bigger and bigger and bigger and bigger and the denominator is staying put, then the value of this ratio is getting larger and larger and larger. If the numerator is increasing and the denominator is fixed, then this ratio is becoming larger and larger. In conclusion, as angle A increases, sine of A increases. Now, cosine of angle A, we know that to be adjacent over hypotenuse, or x over r. Now here, notice what x is doing. X is getting smaller and smaller. As angle A increases in measure, x is getting smaller and smaller, and r is fixed. That means this ratio is decreasing as angle A increases. And we can look at tangent of A as y over x. Tangent of angle A is y over x, remember that? And so the numerator of this ratio is getting larger while the denominator, x, is getting smaller, of course, as angle A increases. So therefore, this ratio is becoming larger and larger in value. So tangent of A increases. So you can see sine is an increasing function. Sine of A, of angle A, will increase as angle A increases. Cosine of A decreases as angle A increases. And tangent of A increases as angle A increases. Now, a similar discussion will lead you to believe that cosecant of A decreases, secant of A increases, cotangent of A decreases as angle A increases. Determine whether each statement is true or false. Tangent of 25 degrees is less than tangent of 23 degrees. True or false? Well, tangent is an increasing function. That means as tangent of A increases, tangent of A increases as A increases. In other words, the larger the angle A, then the larger tangent of A will be, right? The larger A is, the larger the angle, the larger tangent of A. The larger the angle, the larger tangent of that angle. Between these two angles, 25 degrees and 23 degrees, 25 degrees is larger, therefore tangent of 25 degrees should be larger. However, this statement says otherwise. This statement says tangent of 25 degrees is less than tangent of 23 degrees. That's false. That cannot be true. Now for cosecant of A decreases as A increases. Let's make sure we understand what this means. The larger the angle A becomes, the smaller cosecant of A becomes. So the larger the angle, the smaller cosecant of A. Okay, let's look at this. Between 44 degrees and 40 degrees, 44 degrees is larger. Therefore, cosecant of 44 degrees is less in value than cosecant of 40 degrees. And that's exactly what this statement says. So this one is true. All right, guys, we're going to wrap up this lesson with the following topic: trigonometric function values of special angles. Now, there's certain angles that are special for us in our studies, namely 30 degrees, 45 degrees, and 60 degrees. 30, 45, and 60 degrees. They occur so often in trigonometry, and in more advanced mathematics that we're going to look very carefully at these three angles. Okay, so to get us started, we're going to start with an equilateral triangle. Remember that an equilateral triangle is where all of the angles are the same measure, which means they have to be 60 degrees each, so that they all add up to 180 degrees. And all the side lengths are the same. Now, you can choose whatever side length you want. It doesn't have to be 2. I chose 2 just because of what we're about to do. It's going to make the arithmetic just a little easier, but you can choose whatever you want for these side lengths, okay? The first thing we're going to do is we're going to kind of cut this triangle in half, if you will. We're going to bisect one of the angles. So this angle up here, we're going to bisect it. We're going to cut it right in half and make 2 right triangles. Bisecting this 60-degree angle would give us a pair of 30-degree angles, right? So this thing just split in half. And now we have a pair of right triangles. The hypotenuse is still 2 units here. And because we chose 2, then it makes cutting this in half easy. So this is 1 unit and that's 1 unit. What we don't know is the length of side right here, this vertical side, which I've labeled x. But we can use a Pythagorean theorem to find it. So by the Pythagorean theorem, we know that x squared plus 1 squared is equal to 2 squared. That is to say, x squared is equal to 3, which means x is equal to the square root of 3. Okay? So we just found that when we have a, oh, you know what I forgot to label is this angle is still 60 degrees, right? This angle here is still 60. Let me put that in there for us. All right, I got it, you guys. So 30 degrees, 60 degrees, and 90 degrees, okay? So that's the special triangle that you and I are looking at right now. What we want to do is we want to derive all of the 6 trig function values for these angles here, 30 degrees and 60 degrees. We can do that because now we know all the side lengths. We know this is 1, this is 2, and we found x to be root 3. All right, so here we go. Sine of 30 degrees, right? Let's talk about 30 degrees first, okay? So here's 30 degrees. This is my 30, 60, 90 triangle. 30, 60, 90 triangle. Sine of 30 would be opposite over hypotenuse, so 1 over 2, okay? Cosine of 30 will be adjacent over hypotenuse, so root 3 over 2. Tangent of 30 degrees will be opposite over adjacent, 1 over root 3, 1 over root 3. We should rationalize this by multiplying the numerator and denominator by root 3. Will give us root 3 over 3. Cotangent of 30 degrees, cotangent will be adjacent over opposite, root 3 over 1, which is just root 3. Secant of 30 degrees, secant of 30 degrees will be hypotenuse over adjacent, 2 over root 3. But we should rationalize by multiplying the numerator and denominator by root 3. Finally, cosecant of 30 degrees will be hypotenuse over opposite, 2 over 1, which is just 2. These function values are really important. 1/2, root 3 over 2, root 3 over 3, root 3, 2 root 3 over 3, and 2. These are all the trig function values of 30 degrees. What I would like us to do now is to derive all of the 6 trig function values for 60 degrees. But I wonder if we can use what we've studied in this lesson to save us time. So watch this. 60 degrees and 30 degrees are complements. They're complements. So I wonder if we can use the fact that cofunction values of complementary angles are equal. In other words, so sine of 60 degrees will be equal to cosine of 30 degrees. How do I know that? Well, sine and cosine are cofunctions, and 60 degrees and 30 degrees are complements. And cofunction values of complementary angles are equivalent. So this is going to be root 3 over 2. Now you can confirm that if you want. Root 3 over 2. Sine of 60 degrees, right here, sine is going to be opposite over hypotenuse, root 3 over 2. But I'm using this work that I've already done to get all of these. So cosine of 60 will be equivalent to sine of 30. So cosine of 60 will be equal to sine of 30 because cosine and sine are cofunctions and 60 degrees and 30 degrees are complements. So this is going to be 1/2. And you can reference your triangle if you want, but I'm not even looking at my triangle anymore. I'm looking at these function values. Tangent of 60 degrees will be equivalent to cotangent of 30 degrees. Cosecant of 60 degrees will be equivalent to secant of 30 degrees. Secant of 60 degrees will be equivalent to cosecant of 30 degrees. Finally, cotangent of 60 degrees will be equivalent to tangent of 30 degrees. There. So knowing these gives us these. Now the other special angle will be 45 degrees. We just finished talking about 30 degrees, 60 degrees. Now let's wrap this up with a 45-degree angle. I've started us out with an isosceles right triangle. It's a 45-45 right triangle, 45-45 right triangle. We just looked at a 30-60 right triangle. Now this is a 45-45 right triangle. I call it an isosceles right triangle because this side is equivalent to this side. So I have one pair of equal sides. Now we can solve for r, which is just what I called the hypotenuse here. We can solve for r using the Pythagorean theorem. So we know that 1 squared plus 1 squared must be equal to r squared. That is to say, 2 is equal to r squared, or r is equal to the square root of 2. Okay? All right, let us generate the 6 trig function values of 45 degrees. All right, we got sine of 45 degrees. It doesn't matter which one of these 45-degree angles you look at. Let's just look at this one. They're the same. So sine of 45 degrees will be opposite over hypotenuse. So 1 over root 2. 1 over root 2. But after rationalizing, it'll be root 2 over 2. Cosine of 45 degrees will be adjacent over hypotenuse, 1 over root 2, which is root 2 over 2 after rationalizing. Tangent of 45 degrees will be opposite over adjacent. Wait a minute, 1 over 1. Oh, just 1. So that's 1. Cosecant of 45 degrees will be the reciprocal of sine of 45 degrees. So instead of 1 over root 2, it'll be root 2 over 1. Well, that's just root 2. Secant of 45 degrees will be the reciprocal of cosine of 45 degrees. So it'll be the reciprocal of 1 over root 2. That's root 2 over 1, which is just root 2. Cotangent of 45 degrees will be the reciprocal of tangent of 45 degrees. So the reciprocal of 1, which is 1. All right, we just finished deriving all 6 trigonometric function values for 30 degrees, 45 degrees, and 60 degrees. All right, let's wrap this lesson up with this very important table of values. You have your special angles over here on the left, 30 degrees, 45 degrees, and 60 degrees, and each row will be the function values for each of these angles. So the first row will be sine of 30 degrees, cosine of 30 degrees, tangent of 30 degrees, and so forth. Now, we already generated these, so it's just a matter of filling in what you and I just finished doing. Here, I'll put in sine of 30 degrees for us. Sine of 30 degrees, we found a little while ago that it is equal to 1/2. Remember, we had that equilateral triangle that we cut in half? And then cosine of 30 degrees, we found to be root 3 over 2. Now, let's just pretend we forgot what tangent of 30 degrees is. Oh, I forgot. Well, you have a quotient identity that says tangent of theta is equal to sine theta over cosine theta. So if you forgot what this value should be, just take 1/2 and divide it by root 3 over 2. Sine theta over cosine theta. And 1/2 divided by root 3 over 2 will give you what tangent of 30 degrees is, which is root 3 over 3 after rationalizing. Now, cotangent of theta, let's pretend we forgot what cotangent of 30 degrees is. I forgot what cotangent of 30 degrees is. Well, you have a reciprocal identity that says cotangent of 30 degrees is just the reciprocal of root 3 over 3. So if you flip that number over and rationalize, you'll get root 3. Secant of 30 degrees is the reciprocal of cosine of 30 degrees. So that's going to be 2 root 3 over 3 after rationalizing. Cosecant of 30 degrees will be the reciprocal of 1/2, so that's just going to be 2. So had I forgotten these 4 values, I can get them all by just knowing these 2. Now, sine of 45 degrees, we just generated these, and that is root 2 over 2. Cosine of 45 degrees is also root 2 over 2. Now remember, if you forgot what tangent of 45 degrees is, you can use the quotient identity. Tangent of 45 degrees will be equal to sine of 45 degrees divided by cosine of 45 degrees. Root 2 over 2 divided by itself. That's just going to be 1. Cotangent of 45 degrees will be the reciprocal of 1, which is 1. Secant of 45 degrees will be the reciprocal of cosine of 45 degrees, so that's just going to be root 2. And the same thing goes for cosecant of 45 degrees. It'll be the reciprocal of sine of 45 degrees. Now, I just showed you again how, had I forgotten these 4 function values, as long as I knew these first 2, I'll be fine. I can use identities to get the rest. Now, this whole row can be found, the entire row can be found using the first row, because 60 degrees and 30 degrees are complementary angles, and I can use cofunctions. So sine of 60 degrees will be the same as cosine of 30 degrees. So this will be root 3 over 2. Remember, cofunction values of complementary angles are equal. Cosine of 60 degrees will be equivalent to sine of 30 degrees. So that's 1/2. And then tangent of 60 degrees will be equivalent to cotangent of 30 degrees. Folks, I'm using what we know about cofunction values of complementary angles. Cotangent of 60 degrees will be equivalent to tangent of 30 degrees, so root 3 over 3. Secant of 60 degrees will just be the reciprocal of cosine of 60 degrees, so it'll be the reciprocal of 1/2 which is 2. Finally, cosecant of 60 degrees will be the reciprocal of sine of 60 degrees, which will be the reciprocal of root 3 over 2, that being 2 root 3 over 3. So I know this is a lot of information, but what I want to emphasize is if you know at the bare minimum sine of 30 degrees and cosine of 30 degrees, sine of 45 degrees and cosine of 45 degrees, if you know these 4, you can get all the rest using either a reciprocal identity or using the fact that cofunction values of complementary angles are equal. All right, in earlier lessons, we had a table similar to this one, but it was for quadrantal angles. 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees. Remember, that table of values was filled with zeros, 1, -1, or undefined. Now we have this table here. So it's a lot of information. You may want to take really, really good notes if you're not already, and make sure that you're keeping all of this information straight or keeping it really handy and clear and concise in your notes, okay? So the expectation is that you would know really quickly, shall I even say memorized, the expectation is that you would know all trigonometric function values for 30, 45, 60 degrees, and your quadrantal angles, 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees. Please study hard to know really well all 6 trigonometric function values for these special angles and your quadrantal angles. All right, I'll catch you later. Good work, everybody.